Next, let's talk about trawling, which is another method to analyze large graphs. And different from before, in this part, we'll work with directed graphs, and we're interested in detecting communities that take the form of complete bipartite graphs. And the goal of trawling is to search for small communities in the web graphs. So what is the signature of a community or discussion in a web graph? The intuition is that if many people, they all talk about the same things, then they probably form a community, right? And in Twitter, this can be with a set of users tweeting about the same set of hashtags, or on Facebook, this can be a set of users sharing the same set of links. And we can use this community that we discover to define topics. So basically what the same set of people on the left talk about on the right. Remember that this is actually somehow similar to the hubs and authority idea that we discussed about. And more specifically, we can define the problem as enumerating complete bipartite subgraphs KST in a large graph, where KST is actually a subgraph where we have S nodes on the left and we have T nodes on the right, and they are fully connected. For example, if we set S to 3 and T to 4, then this following graph qualifies as a instance inside KST. And interestingly, this problem can be easily solved using our previous frequent item set algorithms, such as the a priori algorithm. And before talking about it in detail, let me remind you that in the market basket analysis setting, which is the setting in the frequent item set algorithms, we have a market, which is a universe U of n items, and we have baskets, which are m subsets of U. So basically, these are S1, S2, all the way to Sn, and all of them are subsets of U. So Si is basically a set of items that one person bought. And we also defined the support as a frequency threshold out. So the goal of a frequency item set algorithm is to find all subsets T such that the items in T were bought together at least half times. So what is the connection between item sets and complete bipartite subgraphs? The answer is that these frequent item sets are actually equivalent to complete bipartite subgraphs. How so? For example, let's see that if, let's say that if a node I is connected to node A, B, C, D, and the key to understand this equivalence is that we can construct a item set according to this graph as a set that contains A, B, C, D. Now let's say that if it turns out that this set A, B, C, D is actually a frequent item set, what does it mean? It means that there were a lot of nodes. There were a lot of nodes that connect to A, B, C, D at the same time. And this is exactly the definition of complete bipartite graphs. And more concretely, let's look at one small example. Let's view each node I as a set Si of nodes that I points to. So for example, if node I points to A, B, C, D, then we can construct an item set that contains A, B, C, D. And we want to find frequent item sets with a minimum support S and a item set size of T. So for example, let's say that we set S and T to 3. Now, and let's further say that we actually find a frequent item set, which is Y, that contains ABC, and it has a support of 3. So that means there are actually S nodes or three nodes that link to all of A, B, and C. For example, it can be a node S that links to ABC, and we have a node Y that links to ABC, and we have node Z links to A, B, and C. And until here, actually naturally found a complete bipartite subgraph, right? And this is the complete bipartite subgraph we found. As another example, let's say that we're given a graph here of 6 nodes, and the next step is to construct item sets as we discussed before. For example, for node A, it's connected to node C, D, and B. Therefore, we will construct a item set that contains B, C, and D. And the same thing happens for B, because B, it only connects to D. Therefore, it will have an item set that contains only D, so etc., etc. And let's say that we want to find a frequent item set with a threshold of 2. And if we run the a priori algorithm, we can find that actually we have 2 frequent item sets. One is the set BD that has support 3, and the other one is the set that contains E and F that has support 2. And we actually found naturally 2 bipartite subgraphs, right? And the first bipartite subgraph is here. And this corresponds to the frequent item set B and D. And since this frequent item set has a support of 3, and we have 3 nodes on the left that has the outlinks. And the second complete bipartite subgraph is here corresponding to the second frequent item sets. We can see that this is E and F, therefore we have nodes E and F here. And since this item set has a support of 2, therefore we have 2 nodes on top here that has only outlinks.